Good morning everyone, my name is Huda bin Karroum and today I'm going to walk you through our research paper called Optimization of LSTM Algorithm Through Outliers, Application to Financial Time Series Forecasting. With a little bit less of jargon, we are here trying to optimize the architecture of a deep learning algorithm known as long short-term memory or LSTM through handling the outliers that are in the input data. So let's start. Our presentation is going to be structured as the following. The first section presents a brief summary of some of the main approaches that have been done to modify LSTM architecture. Then, the second sections explain the approach that we have proposed to improve LSTM forecasting efficiency. Finally, we will use this novel model in a financial time series forecasting problem. Time series are complex to forecast or analyze as they are characteristically nonlinear, non-stationary, and noisy. Hence, traditional statistical models such as Garch, Arch, ARIMA, etc. models have usually failed to capture the complexity and behavior of the financial time series. Therefore, researchers are now using more sophisticated nonlinear technique for time series analysis, forecasting, and classification. State-of-the-art methods for handling these tasks often rely on both machine learning algorithms like support vector machine, k-nearest neighborhoods, and deep learning techniques. Here we're going to propose a novel approach that extends the LSTM algorithm by handling the outliers as a part of the model architecture. LSTM networks are considered as a special type of recurrent neural network and were designed to avoid long-term dependency issue. In terms of the architecture, we have the self state, the hidden state, and three other different gates. First of all, we have the forget gate to decide what information the model will forget and what information it will keep, which then lead us to the input gate. And finally, given the new state of the memory cells, we can calculate the value of the output gate and the hidden state. We will explain further in the next slide the different gates that decide on what info is to add to the cell state. In this slide, we will be detailing how each gate and cell are calculated. Starting by the forget gate, let's first note that all the W and B here refer respectively to the weight matrices and the bias vector parameters that need to be learned by LSTM during the training phase using a sigmoid activation function in the process at this step. Then this leads us to the input gate value and the candidate value for the state of the memory cell at time t. Here we can see we have both a sigmoid function and a 10H function. Let's note that a sigmoid activation function is roughly similar to the 10H activation. So instead of squeezing values between -1 and 1, it squeezes them between 0 and 1, which is helpful to update or forget data because any number getting multiplied by 0 is returned 0. And this causes value to be, let's say, forgotten. Now that we know the value of the input gate activation, IT, the forget gate activation, FT, and the candidate state value, we can calculate CT, which is just the memory cell's updated state at time t. Finally, given the new state of the memory cells, we can calculate the value of the output gate OT and the hidden state HT. Now let's go through some modified versions of LSTM. We will go through LSTM additional mean layer, the ensemble forecasting, and the gated recurrent unit model. One of the popular LSTM variants that have been developed recently is the LSTM additional mean layer, and it consists of adding both mean pool layer and logistic regression to the initial LSTM layer. The model used in this approach is composed of one single LSTM layer followed by mean pooling over time and a logistic regression layer. Then the LSTM ensemble forecasting consists of effectively combining multiple prediction results from a group of individual LSTM networks to produce the prediction output. As the simple averaging approach can be biased by outliers and not reliable for skewed distributions, this proposed averaging approach dynamically adjusts the weights used for combining multiple LSTM models. Here, y hat k denotes the forecasted output at the timestamp k obtained using the LSTM model M, and Wm is just the associated combining weights. So these are the formulas for the LSTM ensemble forecasting. Finally, the gated recurrent unit model is another variation of the LSTM. It uses the hidden state to transfer information while completely getting rid of the self state. It is achieving so by combining both the input and forget gates into a single updated gate noted ZT here. It also measures the hidden state and self state. Now let's move to the anomaly detection section, which refers to identifying the outlier data points present in our dataset relatively to some standard or usual signal, like extreme values that deviate a lot from our observations. We will go through Altman Z-score, isolation forest algorithm, and interquartile range. Altman Z-score is a parametric measure that calculates how many standard deviation a specific data point is from the sample's mean, assuming Gaussian distribution of our data. The isolation forest algorithm is a recursive random partitioning algorithm. It isolates some observations by randomly selecting a feature and then randomly selecting a split value that falls between the minimum and the maximum value. And finally, the interquartile range is a measure of variability of data based on dividing the dataset into quartiles to evaluate how spread out the values are. Now we will go through our proposed architecture. So here we propose a novel LSTM framework for time series forecasting, where we modify the architecture of the LSTM unit by adding a new layer called the outlier gate, which controls the flow of information that goes into the LSTM cell. This added signal allows us to avoid the carryover effects of the outlier on the forecasted point caused by unusual or non-repetitive events, and a bias in the estimate of our LSTM model. So here we have the formula that led to for every one of the gates used in the architecture. The outlier gate is the first one that we have in the first line. In this section, we're gonna present our results and analysis where we have applied our newly proposed architecture to a financial time series dataset. So the dataset that we used consists of financial time series of the volatility index VIX, daily open and close prices, and daily highest lowest prices for the last 15 years. When running the new modified LSTM architecture, we got a root mean square error of 1.5, which was 15% lower than a conventional LSTM model for the same dataset. This modification of the LSTM architecture, i.e. to include an outlier gate, has proven to be more accurate than the vanilla LSTM model. Now, finally, we are in the conclusion. So just to summarize briefly, in this paper we have proposed a novel LSTM architecture where we add an outlier gate that controls the flow of information that goes into the LSTM cell. This added signal allowed us to avoid the carryover effect of the outlier on the forecasted point caused by unusual or non-repetitive events, and also a bias in the estimates of our LSTM model. We then applied the proposed model to a financial crime series forecasting problem. The provided experimental results validate the proposed contributions by reducing the RMSE by 15% and proved the effectiveness of our novel approach by achieving better performance over vanilla LSTM. Thank you for your attention.